This is John Mellor-Crummey. In this talk, I'll briefly introduce you to analyzing GPU-accelerated applications with HPCToolkit. So the outline for this talk is I'll first describe the use of HPCToolkit for GPU-accelerated applications. Then I'll tell you the status of our implementation for GPUs by various vendors. And I'll give a demo of HPCToolkit measuring some data for a GPU-accelerated application on an NVIDIA GPU, using both operation level monitoring, where we're monitoring kernel launches and memory copies, things like that. And then the second demo will monitor using PC sampling, which is a unique capability on NVIDIA GPUs. And I'll conclude by talking about the status of our ongoing work. In a previous introduction talk, I described HPCToolkit's workflow for GPU accelerated applications. So let's look at how to use each of the utilities in HPCToolkit for working with GPU accelerated code. So first, we'll focus on HPC run. How do we measure GPU accelerated programs? So in order to measure GPU accelerated programs, you can profile them by saying -e GPU equals, and then you give it a specification for a GPU implementation. So typically, you say NVIDIA for CUDA, you'll say AMD for HIP, OpenCL, this works on AMD, Intel, and NVIDIA GPUs, and then level 0 is something for Intel GPUs only. And so this will do profiling at the operation level. If in addition you want to collect traces on the GPU stream to show the activity on the GPU, you can just add the -t option. And tracing is supported on all of the GPU implementations except for the one for level 0. For GPU PC sampling, this is a capability that only NVIDIA has. And if you'd like to use PC sampling to monitor the activity inside your GPU kernels, you just say GPU is equal to NVIDIA, PC, and then that will use PC sampling to track various kinds of stalls inside your GPU kernel, and we can provide line level performance information, which is something unique. If you want to combine CPU profiling and tracing, you might say -e real time, and then also give it a -e GPU option and say -t, and that'll be doing tracing on both the CPU and the GPU and collecting measurements for an NVIDIA, AMD, or OpenCL implementation. And then to use this with job launchers, you just do it the way that you use HPC run in general with job launchers, except that you're going to add a GPU option as part of your measurement options. So the way that HPCToolkit fits together with the various GPU software stacks, you can see at the bottom that we have NVIDIA GPUs, Intel GPUs, and AMD GPUs. We have this GPU independent measurement substrate that we provide that works across all the platforms. On Intel GPUs, we can use GTPin for adding instrumentation to GPU binaries. On NVIDIA GPUs, we use the NVIDIA Sanitizer API for some instrumentation. And then on top of this, we have software stacks so that there's CUDA on top of NVIDIA's CUPD layer. And then on top of CUDA is the implementation of OpenMP, and then Cocos and Raja programming models are on top of CUDA. On Intel GPUs, we're using DPC++ and OpenMP, which are implemented on top of the OpenCL and level 0 layers. Raja is implemented on top of DPC++. And then on AMD GPUs, the Raja and Cocos live on top of either OpenMP or directly on top of HIP, and we use the ROC tracer infrastructure from AMD for gathering our performance information. So when we measure executions on GPU accelerated supercomputers, there are several different measurement interfaces we're using. So the hardware provides, on the CPU, we have the performance monitoring unit. On the GPU, we have hardware counters and PC sampling on NVIDIA GPUs. On the software side, we're using the glibc LD audit subsystem for tracking dynamic loading of shared libraries, and Linux perf events can be used for measuring the application with hardware performance counters and also for looking inside the kernel. We're also using GPU monitoring and instrumentation libraries from the vendors. So I mentioned we're using NVIDIA's CUPTI and AMD's Rock Tracer. So there are multiple measurement modalities and interfaces for GPU accelerated computation. So we're using sampling on the CPU. Whenever a GPU operation is launched, we get a callback from either NVIDIA's CUPTI or AMD's Rock Tracer when a GPU operation is launched. So that might be launching a kernel or a memory copy. And sometimes we get callbacks when these operations are completed. And then we are gathering a GPU event stream, a log of the operations that are executing on the GPU. And we're also collecting PC sampling measurements on NVIDIA GPUs. When you use HPC struct to recover the program structure for GPU accelerated applications, as before, you apply HPC struct to the measurement directory. When you monitored a GPU accelerated application with HPC run may have recorded GPU binaries in the measurement directory if you're running a GPU accelerated application. So by default, what HPC struct is going to do is it's going to analyze information in the GPU binary at the source line level, but it won't build a control flow graph and loop nests unless you ask it to. So if you wanted to build a control flow graph for GPU binaries, you can pass the --GPU CFG yes option. The reason why this is an option is that, first of all, it's only useful on NVIDIA platforms at present because we don't have any fine-grained measurement data from other vendors, and therefore we can't attribute performance at the source line level, and therefore analyzing loop nests is pointless. On NVIDIA GPUs, unfortunately, NVIDIA doesn't provide good APIs for getting the CFG information, and we actually have to rely on an NVIDIA utility to compute this for us. So what we end up doing is invoking an NVIDIA utility, dumping the results to ASCII, and then parsing them into HPCToolkit. This can be very costly for large programs. And so if you have a program that has hundreds of megabytes of GPU binaries, if you say --GPU CFG yes, it may run for an undetermined amount of time. So you may find it better to not analyze the GPU CFGs and just get the line level information, which can be obtained rather quickly. So the next step in the workflow is HPCProf and HPCProf MPI. And so you use HPCProf or HPCProf MPI the same way that you did for CPU programs. You just say HPCProf and you run that on the measurements directory. Or if you have a measurements from a large scale execution on a GPU accelerated platform, then you can use HPCProf MPI to analyze the measurements directory. The last step of the workflow is to use HPC Viewer, and it works the same way that it does on CPU accelerated applications. You have both profiles and trace views. Something different is that inside the trace views, you actually have trace lines for GPU streams. So the status of our GPU monitoring support in HPCToolkit is that we have pretty much full support for NVIDIA GPUs in our master branch. We can monitor things like kernel launches, memory copies, synchronization events. We can also do instruction level measurement analysis using PC sampling. And we can monitor things like kernel characteristics, including the register counts and the amount of shared memory that's used in a kernel. And we report those as metrics in the profile view. For AMD GPUs at present, we can monitor the GPU operations like kernel launches, memory copies, and synchronization. For instruction level measurement analysis, there's no support at present. There's some indications in GitHub that AMD is developing some support for PC sampling, but it's unknown when that will become available or what GPUs it might be available for. It certainly doesn't seem to be evident on any of the GPUs that we have at present. There's information about kernel characteristics that's available statically, but we're presently not gathering and reporting it for AMD GPUs. For Intel GPUs, we can also monitor kernel launches, memory copies, synchronization, things like that. For instruction level measurement, there is support for instrumentation using GTPin. Intel has allowed us to say that in the future, they will be adding some instruction level measurement support for GPU code to a future GPU, but we can't say what GPU that might be. It's just some future GPU. Here I'm going to give a quick demo of the capabilities for measurement and analysis of GPU accelerated applications using Lawrence Livermore National Labs Quicksilver mini application. So here I'm in a directory of tutorial examples that I downloaded from GitHub, and I'm in the Quicksilver directory. And so there's a set of setup scripts, and I have one set up for my local machine that will configure some environment variables. And now if I say make build, it will download and build the Quicksilver application. And you can see that it's building it with -O2 optimization and -G to provide the symbol information on the host with line maps for the host binary, and -line info tells it to include line mapping information in the GPU kernels. I'm building this for an NVIDIA A100, which is the architecture that I have here. So now for this example, I can say make run, and it's running the application with HPCToolkit. And then, so we'll look back at the commands that are being run in this script. So it's saying HPC run and putting it into an output directory, and we're measuring real time eGPU is equal to NVIDIA, and we're also collecting traces. So this is doing operation level measurement of the Quicksilver application. And so then after it measures the execution, then it's applying HPC struct GPU CFG no to the measurement directory. And so it analyzes the GPU binary that's included inside. And then and we use HPC prof to analyze the measurement data. And now I can say make view. And this is bringing up HPC viewer, and we have the activity in the program. And so I have GPU kernel operations. I can see that all of the kernel operations are launched by the main program, and I can show where they are. And in fact, the main thing is the cycle tracking kernel that accounts for 100% of the GPU activity. That is this is the 100% of the kernel launches are this. There's only one kernel in the application, and all of the interesting calculations are inside that kernel. I can look at the trace, and what I have on the CPU is I have call stacks for things on the CPU, and then for the GPU, it shows me a full call stack and shows me that I'm launching cycle tracking kernel. And so you can see that in the different launches of the kernel, it's starting out with long kernel execution, and then there's a period of shorter kernels, and then the kernels get very short as we get to the end of a phase. And so that's really the only thing that we can see of interest by looking at the GPU trace here. So in this case, it's not very interesting. It's also showing that the GPU is not active all the time. These white spaces mean that the GPU is idle. And so while certain things are going on the host, the GPU is idle. So here's this phase where it's doing population control as part of this population control guts as part of the Monte Carlo simulation, and no GPU activity is initiated by this routine and none is overlapped by this routine. So if that could be overlapped with computation on the GPU or offload computation on the GPU, that provides an opportunity for improving this by keeping the GPU more active. Okay, so now let's look at the other example. So I'm going to run it again, and I'm going to use PC sampling to monitor it. So this is the PC sampling currently slows down the execution significantly. And so I'm running a smaller problem here to finish in modest time. And now I'm analyzing the CFG inside the kernel, because since we have measurements for the individual instructions, we want some finer grain attribution inside the GPU kernels. I'll say make view-PC to look at the PC sampling information. And in this case, we just collected information on the GPU side. We didn't actually collect any information on the CPU side. So the first column that comes up is GPU instructions. And so I'll just drill down and show where the GPU instructions are. Now we can see that we're invoking this GPU kernel, cycle tracking kernel. And then inside it, there's a call to cycle tracking guts on line 132. And there's a loop inside that. And inside that, it's calling a GPU device function collision event. And so this is something unique. We are collecting PC samples as the program executes, and then we are reconstructing a call graph on the GPU based on looking at the static call graph and understanding where the calls to various functions are. We can determine that we can recover either exactly or approximately what the calling contexts look like and attribute cost to them. So inside this collision event, we see that there's a loop, and then there's another loop nested inside that. There's calls to this microscopic cross-section. And so what you can see is that using the PC sampling, we have an awful lot of data inside the GPU. We're attributing things to source lines and to inline code and to loop nests, much the same way that we do on the CPU. So another thing we have, besides just knowing where the instructions execute, is we also have information from NVIDIA's PC sampling hardware that tells us where stalls are in the code. And so I'll switch to the flat view, and we'll focus on where most of the stalls are. And so we can see here that 22% of the stalls are associated with nuclear data, and that the stalls are inside this get reaction cross-section, and the stalls are principally associated with this nuclear data line 253. And we can see this multiple levels of indirection in a subscripting calculation. And if we look at all of the stall metrics we have 5 times 10 to the 9th stalls here. And if we scroll to the right to look at the metrics, what we'll find is that the memory dependencies that the stalls waiting for global memory account for 4.5 times 10 to the 9th. So this is the largest fraction of the stalls are explained by stalls waiting for global memory, which is the kind of thing that you would expect with multiple levels of indirection. So that basically showcases our PC sampling capability and what you can find out from it. One last thing is in the top-down view, if we go back to the GPU kernel, we also have some static information about the kernels. And so over in columns off to the side here, we have information about the fine-grained parallelism that's available and how much of it is active. And so this is showing that we're only using 1/4 of the fine-grained parallelism. So this is the number of warps that are active. We have the registers that are in use inside the kernel, the number of blocks, and the kernel count. And then we have something here that says that we have 25% occupancy, which means that we're using 1/4 of the resources inside the GPU. So we could be using more threads. So that's an opportunity for improvement. So then the question is, why can't we use more threads? And that probably has to do with resource consumption, like register footprint used by the kernel. All right, let's go back to the slides. I'm showing a trace view for a large scale execution on a supercomputer. And this is collected on 128 nodes. It's got AMD processors in it with 4 NVIDIA A100 GPUs per node. And so the execution is 512 ranks and 512 GPU streams. There's a lot of data here. So you can see from the mini map that, in fact, we're looking at just a very tiny slice of this execution. The entire execution is a little over 4 minutes long. And what we see here is for the selected operation where we have the cursor, we're able to see the full call path to the GPU kernel and where it was launched. And we're also able to see that this is going through Cocos Parallel 4 operations that are launching things on a GPU. I'll conclude with some remarks about our work in progress for improving support for measurement and analysis of GPU accelerated applications. On Intel GPUs, currently we have support for OpenCL and level 0. Our support for OpenCL is a little bit more full-featured, and we're trying to transition that support into level 0, which is Intel's planned premier runtime system. So currently, we're using GTPin for fine-grained measurement. We can measure instruction counts using GTPin, but there are some capabilities that have been developed in a branch that also measure things like scalar instructions and vector instructions, and those capabilities are not yet deployed in our master branch. And so we're working to integrate those so that they can be released. On AMD GPUs, we're working with the University of Wisconsin on binary analysis and instrumentation for fine-grained measurement and attribution. Currently, there's no support for fine-grained measurement on AMD GPUs. On NVIDIA GPUs, NVIDIA released new support for recording information about inlining in their GPU kernels, and we've developed a prototype that exploits this to attribute the performance and at a finer grain inside GPU kernels. We have a set of patches that we need to distribute to the community. There are patches for Red Hat's ELF-utils and also for the University of Wisconsin's Dynast. And those patches need to be accepted before these capabilities will be in a released version of HPCToolkit. We're also working on reducing the fine-grained measurement overhead with some new capabilities that NVIDIA developed for low overhead PC sampling. In terms of improving the scalability, one of the scalability problems for monitoring with GPU accelerated programs is that we're monitoring lots of metrics. So it might be as many as 100 metrics when we're monitoring GPU accelerated applications. And it turns out that those metrics are very sparse. They only apply to the GPU code in the execution and not to any of the CPU code. And so if we don't exploit the sparsity, then the data sizes can end up being larger by as much as a factor of 1,000. And so we have a new version of HPCProf MPI that uses massive threading to analyze data from large-scale programs. And it also uses sparse formats, which are important for managing data for GPU accelerated applications. And so we expect that to be integrated into a release in the near future. On the user interface, we're looking to overhaul our metric view to enhance its performance and scalability. And so that work is nearly complete. We have some additions to our trace viewer that associate trace lines with metadata. So the node, the GPU, the MPI rank, and the GPU stream. There's a little more work that's necessary on that to make it more usable. And we're working on improving the presentation of the many GPU metrics. And then finally, the other thing that's been a focus of a lot of work is to just improve our reliability and completeness on GPU accelerated platforms.